Welcome to the first set of video notes for Unit 9. Unit 9 covers stoichiometry, which is a long and scary sounding word, but essentially just means if I tell you how much of a certain reactant I have, or how much of two reactants I have, can you use math and your knowledge of chemistry to figure out how many products would be formed? So again, that's stoichiometry, and in today's notes we're going to focus on I can statement 9.1, which I'm writing out for you. And 9.1 focuses specifically on chemical quantities. And really, chemical quantities is just all about the mole. And so in today's notes, we're going to talk about what the mole is and how we use the mole in different calculations. So in the English language, we have many words that are used to represent numbers, words that equal numbers. For example, if I said the word pair, not P-E-A-R, but P-A-I-R, you would think of the number 2, like pairs of socks or pair of shoes. If I said the word dozen, you would think of the number 12, like a dozen eggs or a dozen donuts. If I said the word score, you might not think of the number 20, but that's like 7 years ago. That's a little lesser known one. Gross, that's 144, like a gross of pencils. This one you're probably more familiar with. A grand, you would think of the number 1,000. And this was another fun one that you might not know. Myriad, represents the number 10,000. So anyway, hopefully you get the point that we have a whole bunch of words that we use to represent numbers. Well, mole is just a word that we use to represent a number, a very specific number. That number is 6.022 times 10 to the 23rd. And this is an insanely huge number, but it's used to represent insanely small things. When we talk about a pair, we're usually talking about socks or shoes. When we talk about a dozen, we're usually talking about donuts or eggs. When we're talking about a mole, we're usually talking about atoms, ions, or molecules. And keep in mind, these things are tiny. So if you have a mole of something, you have 6.022 times 10 to the 23rd of that thing. If I had a mole of marshmallows, I would be able to cover the entire earth in marshmallows miles deep. So this is an insanely huge number. This number is actually called Avogadro's number, after Amadeus Avogadro, who came up with a mathematical equation that featured this number. So again, insanely huge number that represents insanely small particles. So let's put this into practice. If I have 1 mole of a substance, and by the way, we usually use lowercase m-o-l to represent a mole. So if I have 1 mole of a substance, let's say 1 mole of carbon atoms. What that means is that I have 6.022 times 10 to the 23rd carbon atoms, which is actually, a single carbon atom is so small you wouldn't even be able to see it. But if I gave you a mole of carbon atoms, you would be able to physically see that and touch it and hold it in your hand. It's probably, about 12 grams of a substance, so you would be able to see it. If you have 1 mole of sulfur, again, it's another element, 1 mole of sulfur atoms, that means you have 6.022 times 10 to the 23rd atoms of sulfur. And again, this would be a sample that you'd actually be able to see. A single sulfur atom you wouldn't be able to see, but a mole of sulfur atoms you could see and measure. This is why this is a useful number. Now, what if instead of 1 mole of sulfur, you had 2 moles of sulfur atoms? How many sulfur atoms would that be? This is actually pretty simple. All you would have to do is take 2 and multiply it by Avogadro's number. So if you have 2 moles of sulfur atoms, it's going to be 2 times 6.022 times 10 to the 23rd. And if you plug that into your calculator, it's going to be 1.20 times 10 to the 24th atoms. So this would just be like if I said I'd like 2 dozen donuts. That's 2 times 12. If I want 2 moles of sulfur atoms, that's 2 times 6.022 times 10 to the 23rd. We can use even more complex numbers, like 1.5 moles of sulfur atoms. The equation doesn't change. Our method of solving this doesn't change. So think about it. How many sulfur atoms would you have if you had 1.5 moles of sulfur atoms? Just like in the question above, we'd simply multiply Avogadro's number by 1.5. So if I said I wanted 1.5 dozen donuts, I would want 12 times 1.5, which would be 18. It would be a dozen plus a half dozen. These relationships don't change if we're talking about molecules versus atoms. If instead of a mole of carbon atoms, I have a mole of water molecules, how many water molecules are present in a mole of water molecules? It would be 6.022 times 10 to the 23rd water molecules. If I had a more random number, like 3.14 moles of water molecules, how many water molecules would be present? Again, the relationship doesn't change, the formula doesn't change. We're still talking about a mole of something, so all we would do is take 3.14 and multiply that by Avogadro's number. It doesn't matter that 3.14 is a much messier number than 1 or 2 or 1.5. The formula remains the same, and we can still solve these problems. And one other thing to draw your attention to, and I actually just underlined it. If you want to shorten the word molecules to something, don't shorten it to MOL or MOLE, because then it'll be confused with mole. Shorten it to MOLEC, molec. That way you don't have to write the whole thing, but you can shorten it out. Okay, I'm going to end these notes with a challenge problem for you, and I'm actually not going to work this problem within the video notes. I'd like you to attempt this problem on your own. And I will be checking that you at least attempted it when I check your video notes. So copy down this problem into your notes, solve it, and I'll check it when I see you.